Okay, so this is going to be a very unique problem where we're going to have to convert from a log to an exponential. We're going to convert from a logarithmic problem to an exponential problem. So the way that I like starting off with this is that I like to say the term log base 3 of x equals to 4. So I recognize my base is 3, and that will also convert into my exponent. In my exponential form, my base will also be 3. And now I just know I go in a counterclockwise rotation. So I know 3 raised to the 4th power is equal to a value of x. 3 to the 4th power is equal to a value of x. So it solves here. We get 81 is equal to a value of x. So that's going to be our solution for x. And just as a quick conversion, if we know we have let's go ahead and start with the exponential form. A to the x is equal to y. Just like we said before, our base here is a, so the base of our log will also be a. A of y going in counterclockwise direction, a of y equals 2. So we're going to go a of y equals 2 x. So that's the same exact way that we are going to go ahead and solve this in our form. So just being cognizant of that will make it pretty nice. But yeah, hopefully this helps, and then we will continue. Okay, on to our next problem. So determine the domain and range of the following functions. So here we have f of x is equal to log base 3 of x minus 4. So if we were just to have a basic understanding of our log base 3 of x, we know that he's going to intersect here. So this is going to be at 1 comma 0. This is going to be at 1 comma 0. And he will continue on forever and ever and ever. So this will be log base 3 of x. So we know there's one interesting fact about ranges. So the ranges of all logs are always y such that y exists as any real number, or you can say from negative infinity to positive infinity. The ranges always start off somewhere down here at negative infinity and go some out here to positive infinity. So it goes all the way down and keeps going all the way up forever and ever and ever. So, but we know with logarithmic functions our argument must always be positive. Therefore, the domain of this guy must be restricted. So we know that this argument, x minus 4, must always be greater than 0 because we know at 0 there's a vertical asymptote that exists here. So we're going to add 4 to both sides, and we get x is greater than 4, and that will be the domain of our function. We can write that in the form of x such that x must be greater than 4, or in interval notation from negative infinity to 4, not including 4, all the way to positive infinity. So each one of those are sufficient ways for us to write the domains and ranges for this function. So the domain here will be one of these two ways. This guy is set notation, so the guy's interval notation, and the range here is either one of these notations. So knowing your logarithms and your exponential functions can definitely help solve solutions very rapidly when it comes to taking exams. So let's go ahead and look at number 31. So we want to express as a single logarithm and if possible simplify. So we're going to express this as a single logarithm. So in the last two videos we went over log properties, so I'm not going to focus on those. But again, if you are not familiar with this, look up some of your logarithmic properties. So first thing I recognize is that all of my bases and my logs are the same. So I know I'm able to manipulate and combine them. So first thing I'm going to do is that I'm going to distribute this 2 to everything inside the parentheses. So this 2 gets distributed to this, and it gets distributed there. So we're going to have plus 2 log base a of 3x minus 2 log base a of 2z squared. So now since I distribute that 2, I can bring this 2 up as an exponent, and I can bring this 2 up as an exponent. I'm going to leave the negative here. Some people may want to bring the negative in, and that would work just as well. However, I prefer to leave the negative the way I see it. So I'm going to have log base a of 3x plus log base A of 3x quantity squared minus log base A of 2z squared squared. So I can simplify this further as log base A of 3x plus I'm going to square 3x. So 3x squared is really 3x times 3x, which will give me 9x squared. So here I'm going to have log base A of 9x squared. So be careful, 2z squared is really 2z squared times 2z squared, which will give me 4z to the fourth. So I'm going to have minus log base A of 4z to the fourth. So now, since I have gotten rid of all those coefficients and made some very nice arguments that are very easy to manipulate, I can go ahead. I'm going to work through this step by step. I realize here I'm adding two logs with the same base. Therefore, I know I can multiply. Their arguments. So this will give me log base A. 3 times 9 gives me 27. X times x squared gives me x cubed. Minus log base A of 4z to the fourth. And now since I'm subtracting two logs, I can divide their arguments. So this will give me log base A of 27x cubed all over 4z to the fourth. So I've in essence worked backwards in the problem that I did prior, and now we've combined this into one simple log. So we've combined this into one single log, and this is a one single log. Continuing, we want to determine the domain of the zeros of this function. If we want to find the zeros of this function, we're going to set our numerator of our function equal to 0. We can solve this by factoring, and we get x plus 1 times x minus 1 equals to 0. X squared minus 1 is the difference of two squares. The difference of two squares. So a squared minus b squared equals to a plus b times a minus b. Definitely go back and review your formula for the difference of two squares. And if we want to determine the zeros, we set our numerator equal to 0. If we want to find vertical asymptotes, we set our denominator equal to 0. If we want to find horizontal asymptotes, we're going to look at the ratio of the we're going to look at the degree of the numerator in regards to the degree of the denominator, and then there's three different outcomes from that. So from this point, we can now set x plus 1 equal to 0, and we can set x minus 1 equal to 0. So we get a 0 at x equals to negative 1, and then we get a 0 at x equals to positive 1. So in this circumstance, we are going to have a crossing or a touching here, and a crossing or touching here at 1 and negative 1. Continuing on, we want to determine the domain and range of the following functions. So f of x is equal to 3 plus e to the negative x. So first of all, we remember the domain of all exponential functions is all real numbers. So the domain of all exponential functions, they are always continuous. They are always all real numbers. So this is going to be the graph of, we'll just say this one, of a to the x, where a is greater than 0. So where a is greater than 0. Well, a is greater than 0 here, but we will say that x is positive, so x is a positive value. So I should say x is positive, not a is positive. So x is positive, and then down here I will show us what happens when our x value is negative. We're going to have a negative growth or a serious decrease. So this will be a to the x, where x is less than 0. So we could say a to the negative x. So noticing here we still have a domain that's all real numbers. It extends from negative infinity to positive infinity. So we know the domain of this guy. The domain will be x such that x exists as all real numbers, or from negative infinity to positive infinity. And now the range of this function, we must recognize how this function has been transformed. Before, we know the range of this function would start at 0, and 0 would not be included because we have a horizontal asymptote. Would start at 0 and then go all the way to positive infinity. Starts down here at the x-axis, continues all the way up to positive infinity. This guy starts here at the x-axis, continues all the way up to positive infinity. However, notice here we have a value of plus 3. there is a vertical shift So in this circumstance, we have a vertical shift, and that vertical shift is a positive 3-unit shift. So we are going a vertical shift up 3 units. So in essence, what's really happening, and this is just a quick depiction, this is nothing super special, is that in this circumstance, we are going to go up 3 units. So our horizontal asymptote no longer exists at the x-axis. The horizontal asymptote now is shifted up a positive 3 units. So now, instead of intersecting at 0 and 1, which is where we intersected before, over here, now we intersect at 0, comma 4, and our range of this function starts now at this value, which will be a value of 3, not included, and go all the way to positive infinity. If you want to write that in set notation, we would say, in set notation, this would be the value of y such that y is greater than 3.